The document presenter and I are having a little fuss with fuzziness, so I'm having to write large and dark. I hope it will work out. In the last class, you worked with vertical transformations, that if it was y equals the opposite of the original sign values, that just turned the graph upside down, a vertical reflection across the x-axis. And if we had a number tacked on the end, plus 4, say, that was just a vertical translation. Made the whole graph rose 4 spaces up. And we could make it go 4 spaces down. Just to take the whole infinite wave and lift it up 4 spaces. You also had changes in the amplitude. If there was a constant multiplier out front, hope you can hear the Star Spangled Banner out there. So that made the graph go 3 times as high. And also 3 times as low. So today we're supposed to apply those same sort of philosophies to the horizontal changes instead of the vertical, where we change the input values. And if you remember from what we did back in January, the x's behave backwards. If we are going to double the input value, then the x's figure, they only have to be half as big and still get the same job done. If we are going to subtract from the x value, well then the x's, you're going to take something off of them. They have to add more on just to accomplish the same goal. So instead of moving to the left of its subtraction, it's going to move to the right. So let's see what happens when we try it on actual sine and cosine graphs, which I am so sorry about the focus. Let me try again here. Oh my, that's so much better. So if we have y equals the sine of the opposite of theta, where the opposite sign is being applied to the input angle. Well, then the sine of 90 degrees is going to be the same as the sine of negative 90 degrees. So this is going to be down here. And 180 degrees is going to have the same value as whatever negative 180 degrees has. So that would be right here. This whole thing is going to get reflected across the x-axis. So this point is going to get reflected over here. This point gets reflected over here. The 180 gets reflected over here. This whole thing is just going to flip-flop. And we could continue with it all the way across. Just reversing the original sine function, taking this whole infinite thing and flopping it over. Some of you may have noticed that this is the exact same graph that you got last week when you took the negative of the sine of x. And it turns out that this is one of those functions that does that. If you take the opposite of the input value, it's going to equal the opposite of the result. How about the cosine graph? If we do a horizontal reflection across the y-axis here, and I think I may have said x-axis up here, I'm sorry, across the y-axis here. So we'd be taking the cosine of the opposite of the angle. Well, the opposite value at 0 is still going to be the same. It's not going to go anywhere. If we put in an opposite 90, that means this point's going to reflect here. If we put in the opposite of negative 90, that means this point's going to reflect here. And the 180 is going to reflect over here. And it turns out when we start connecting the dots, we have the exact same graph. Nothing changed. And we had that happen before. If we had your standard parabola and you reflected it across the y-axis, nothing changed. Same thing for the absolute value graph. It looked the same when it was reflected sideways. It just turns out that the cosine of negative x is the same as the cosine of positive x. And they're thetas, I know, I call them x's. So that's the basic reflections. Another simple transformation will be the translations. Now when we added it onto the sine values, it moved them up and down vertically. Took the whole wave, moved it up so many spaces, moved it down so many spaces. This one's going to be a little different. So if y equals the sine of theta minus, I'm going to do theta plus 45 degrees. If it's in with the input values, it's going to be acting in reverse. If we're going to add 45 degrees on immediately, theta says, well, I can just drop back 45 degrees and end up in the same place. And that's what's going to happen. So at negative 90, we put in 45. We'll be here at negative 45 degrees. So this value is just going to move over to here. The whole thing is going to move left by 45 degrees. It used to be at 0. That's what's going to move to 45. The value that used to be at 45, that's going to move left to 0. The value that used to be at 90, that's going to move left to 45 degrees. The whole graph is just going to get shoved over to the left by 45 degrees. That's all. So this is going to get moved over to by 45 degrees, and this gets very tedious after a while, but they're all going to get moved over by 45 degrees. I'm not drawing this very well. So the whole graph is just going to get slid over by 45 degrees. For the sake of time, I'm not going to plot every single dot here. I'm just going to kind of wing it. How about if we have y equals the cosine of theta minus 90 degrees. So that means we're going to be subtracting 90 degrees off every single angle we put in. In order to get the same job done, they're going to have to move up 90 degrees. So this thing is going to be moving to the right by 90 degrees. So whatever value we have here at negative 90, it's going to have to move over by 90 degrees. And this is going to move over to the right 90. And this one's going to move over to the right 90. And this one's going to move over to the right 90. And this value is going to move over to the right 90. And this value is going to move over. You get the idea, I think. Excuse me. So this would have been down here. That'll move over to the right 90. Trying to make a nice smooth curve. Miss Milburn said she didn't want any pointy curves. Now some of you may have noticed that when we moved the cosine graph over by 90 degrees, we actually got the sine graph. And we could take the sine graph and move it to the left by 90 degrees and we'll end up with a cosine graph. They are very much related to each other. So the translations to the left and the right, they're not bad. We have another type of transformation, and those affect the multiplications. Now with this, last week, put 3 out in front of the cosine function, and it just made it go 3 times as high, 3 times as low. It's going to be a little different with when we put the 3 as a multiplier in with the input value. So if we have the cosine of 3 times x, this is going to affect the period. This is not what the period's going to be, but this will affect the period. And it will affect it in reverse. Instead of making it 3 times as wide, it's going to make it 3 times as narrow. We're actually going to be dividing by a factor of 3. I forgot to mention that those sideways things were called phase shifts. I'll get back to it. This is sometimes called the frequency. And these are all terms from wave theory. Because these sinusoidal waves, as they call them, and because the original function was the sine function, that's where they get the name sinusoidal. They're everywhere. I mean, our lives are full of them. You could not see, you could not hear if you did not have wavelengths. All our light and sound have wavelengths. Radios, TVs, microwaves, they're very nice wavelengths, very convenient. It's not just the wave action on the ocean that keeps the surfers busy. The waves are everywhere, and we use them. The high frequency things we use as cutting tools, and I wish that we had time to actually explore some of this, and I hope you'll get to study some of them in your future math courses. Anyway, this is the frequency. For this particular one, it says that there will be 3 full cycles in the original period. And as I'm sure you recall, for the cosine and sine functions, the original period was either 360 or 2 pi. So instead of getting 1 cycle, take 360 degrees, we're going to get 3 full cycles. in that same amount of time. The wave is moving 3 times as fast. Another interpretation of it is how it affects the period. The new period on the function we've got here is going to equal the original period divided by 3. So if the original period on the on the cosine graph is 360 degrees, or if it's 2 pi, it doesn't need 360 degrees to get the whole job done. It only needs 120 degrees. So this new function is going to have a shorter period, and we'll get more cycles in the time that we used to get in only one cycle.